Hi, I'm Bucket Hat, and I'm making my gear. What's up? What up? What up? Hi, welcome to part 9 of the ESP32 sampler. We're here. I've got some really good news. I persevered last week. I said to myself, there has to be a way for this microphone to sound better. There has to. So I jumped on the information superhighway, found a GitHub repository and video by an individual by the name of Atomic14. Now, this person has a very informative video describing how to use the internal analog to digital converter on the ESP32 with what is known as DMA, or direct memory access mode. So what I've done is I've used his video and his GitHub repository, and I've cut and pasted my way to a working sampler that sounds way better than it did before. The coding part of this video is going to be intense, and I'm going to do my best to explain what's going on. But as I've said in the past, I'm not an expert at programming. I'm a student of the game. I'm like 50 Cent back in the early 2000s. There's going to be things in the video that I might not explain clearly enough, that I might not have the full grasp and understanding of. So I'm going to do my best here, okay? If I screw up, please leave a comment below. If there's anything that you have any questions about, go check out Atomic14's videos. You know, they're very thorough, very informative, okay? So let's get into this code because it is a lot different than it was last week. All right, welcome to our new code. Before we get going, I just want to mention that the reason why we switched from analog read and the way that we were acquiring the audio data before, because that way of recording audio is actually really inefficient. Every time that we were calling to get an audio sample, the chip has to set up an ADC, convert the signal, and return a value. So that takes time, right? The problem is that the program can't really do much else when it's doing that. And so samples get dropped, recording quality isn't as good. So this method uses the ESP32's I2S peripheral, and I2S is specifically built for audio streaming. It works with the direct memory access to move data between the ADC and memory, all while keeping the CPU free to do other stuff in your main loop. It's just so much more efficient way of acquiring the data. To start things off, we actually have a few libraries that we're using this time. ADC.h, I2S.h. This gives us direct control over the ESP32's hardware for fast, precise audio input and output. So instead of the way that we were doing it before, where it was slow and clunky, this is like way faster. Then we have ESP ADC Cal. This helps us calibrate the analog to digital converter. Basically, just helps us make sure that our audio voltage readings are accurate and stable. That's it. Then we have math.h, which lets us do our math operations. That'll come later when we're applying fades and stuff to the beginning and end of samples. And then I've actually made one myself here called debug macros. And all it is, it's a way of turning our serial output to turn it on and off really easily. That's all it is. And I've included this in the Medium article as well. So as you can see, if we set this to 1, all our debugging information will be present when we're plugged into the computer. If we set it to 0, we turn it off and it doesn't get added to memory. It's a really cool way of saving some space as well. All right, next up, we've made a few changes. I've actually upgraded the sample rate for this particular sketch. For whatever reason, I was getting a lot of compilation errors when I had a lower sample rate. So I've upped it to 44.1. But since then, I've been able to mess around with it a bit at other lower sample rates. So that's something that we can experiment with in the future. But for right now, I'm going to leave it at 44.1. And then the final thing here is we open up an I2S port on the ESP32 at number 0. If you've been following along for a while, you'll say, hey Dave, where's the input pin for the microphone? Well, when we're using the I2S peripheral in ADC mode, the hardware takes care of the routing of the internal ADC input automatically for us. So we don't even have to declare the pin anymore. We just leave it connected to the same pin as before, which in our case is 36. Then we've got this line here, which is our dynamically allocated buffer for our 8-bit audio. We've got our usual LEDs and our rows and our columns. All the stuff is the same as before. Our record pin, record buttons, all the same. We've got our toggles here for looping mode playback. We've got define target sample rate. This creates a macro alias for the sample rate used in the system. Playback block size 256. This defines the size in samples of a block of audio data being processed during playback. This line here declares an enumeration for managing the I2S peripheral state. Mode none means that the I2S is idle or disabled. Mode recording, I2S is in input mode, capturing audio, and mode playback is I2S is in the output mode, playing audio. And then we've got this line here. This initiates the current I2S mode to mode none, indicating that the system starts in an inactive state. And then we've got this flag here, which is used to track whether the I2S driver has been installed or initialized. And it prevents repeated initialization and allows for safer start-stop transitions. We get to the setup, and it's mostly the same, except now we have this. Setup I2S recording. And all this is, it's a declaration that prepares the ESP32's I2S driver in recording mode. Then we know all this stuff. We've done all this stuff all the time. It's nothing's changed there. Then we are into our loop, and everything is pretty much the same here, actually. Nothing has really changed much. We've got our debugging that is different. That's the one thing that looks different, doesn't it? That's pretty much all the same. But then we've got this stuff for setting up I2S recording. And this is what was really a real challenge. Let me just back out here. The best way that I can describe this section is basically installing our driver for recording in I2S mode. Okay, so next we have our start I2S recording, and this is basically configuring the ADC and getting it ready to record. And the ESP32 is really picky about when things happen and what gets disabled and what gets enabled, and it took me forever moving lines around to figure out when the DAC had to be disabled, for example, and when this port had to be open, and it took a lot of playing around with, but a lot of this was lifted from other projects, so I don't really have a deep understanding of how this setup actually works. And the same thing is with playback. When you're toggling to playback mode, this is what's initiating playback mode and configuring playback mode. So it's like disabling the ADC port, enabling the DAC channel. I had to really fiddle with things, and I really don't understand any of this configuration stuff. As I said, like, I just kind of lifted it from other code that people said worked. The record audio function is a little bit different this time. The I2S hardware might be running faster than we actually need. The decimation part just means we skip samples to bring the sample rate down, right? So if I2S is running at 44.1 and we want 11, we can do that. But since our target sample rate and our I2S sample rate is the same, this doesn't really come into play, but it will come into play later when we play with the sample rate a bit more. Okay, then we've got this section here. The recording's begun, okay? And we keep reading blocks of audio until we've filled up our memory. I2S read here is grabbing chunks of audio data. The cool thing about this little function right here is that this is all done in the ESP32's DMA, okay? This is all done behind the scenes. So it really frees up a lot of memory for things to operate efficiently. So we've got our recording done. So here we add 32,768 to shift our sample from a signed into an unsigned range. Then we shift right by 8 bits, dividing by 256 to squash it down into a 0 to 255 range. and that's our 8-bit value. Then each converted sample is saved into raw audio data buffer, and once we hit our target length, we stop. And this new debug line is printing every 1,000 samples. So it's super handy to make sure that everything's working properly. And then we have to shut off our ADC port, and then do our LED stuff, and then print the line saying, hey, switch back to playback mode. And then we go into our handle audio playback, which again is different. So now we're setting up a fade. We've got to fade in and fade out our sample, right? Otherwise we'll get clicks at the start and the end. So what we're doing is we use a smooth cosine fade in and fade out to soften those edges, okay? And it's all done by this math. Again, this is stuff that I, lifted from existing code. This math is beyond me at this point, okay? Once the buffer is full, we write to the DAC with I² S write. And again, DMA is used on the DAC, right? So, because this is also handled by DMA, playback across the keypad is way smoother than it was before. Yeah, that's pretty much all the new stuff. Some of this code, like I said, it's hard for me to wrap my head around it, so I hope I did okay explaining everything. The more important thing is, let's hear what this sounds like now. Okay, let's do a test. Let's test this out, shall we? I'm going to say something into the microphone, and then we will play it back. Eat my shorts. Eat my shorts. Eat my shorts. Eat my shorts. Eat my shorts.
Eat my shorts. Eat my shorts.
Get bent.
Get bent. Get bent. Get bent.
Don't have a cow, man.
Don't have a cow, man. Don't have a cow, man. Don't have a cow, man. Don't have a cow, man. Don't have a cow, man. Don't have a cow, man. Don't have a cow, man.
Ay caramba.
Ay caramba. Ay caramba. Ay caramba. Ay caramba. Ay caramba. Ay caramba.
There you have it. It works so much better than it did last week. You can actually understand what I'm saying now. It doesn't sound terrible. I'm pretty happy with that. So what do we want to do next week? I really want to start digging into a couple things. We need to optimize some of these functions that we have going on the ESP32. We need to double check like the tuning across our keypad matrix. I'd like to tweak the recording function a little bit just to make it a little bit different and a little bit more user friendly. And I'd also like to try adding polyphony. So anyways, I hope you enjoyed this video. I hope I did okay. Let me know in the comments. If what I'm doing here interests you, subscribe to the channel. If you've subscribed already, thank you very much. But yeah, thanks for watching. I'll see you in the next video.